standard apparatus that you can use to measure the Young's modulus of copper wire. So first of all, let's think about some of the theory. Well, Young's modulus is also known as the engineering modulus, and therefore it has the symbol E. And you can calculate Young's modulus by looking at the ratio between stress and strain. And that's provided that the material is behaving elastically, and we have this nice linear region at the first part of its extension. So this is its tensile stress and its tensile strain. How do you work out stress? Well, stress is equal to the force per unit area, which is effectively its internal pressure, divided by the extension over the original length. And sometimes we can use E for extension, sometimes X is used for extension, and sometimes it's delta L. But for the sake of this video here, I'm going to use E to be my extension. What's the force maybe that is being this copper wire being put under? Well, the force is provided by the tension, which is caused by the masses on the end down here. And they've got a weight acting down, which is equal to mg. So that means then that the force is equal to mg. And also we need to maybe think about the area of that wire. What's the area? Well, if we want to find out the area, we need to measure the diameter. And what is really important is that you measure the diameter 3 times in 3 places to make sure that it is truly a circular kind of cross section. So again, the area is equal to pi r squared or pi d squared over 4. Okay, so what we can then do is we can take this equation here and we can rearrange it. We can bring the L up, we can bring the A down, and what we can say is that Young's modulus is equal to mgl over A multiplied by E. So all we need to do then is add some mass on the bottom. We've got a certain length of copper, which is going to get longer. We can measure the extension, we measure the area, and then we can use that to work out Young's modulus for, in this case, copper. So in terms of the equipment setup, it's going to be set up on a long tabletop, and the key thing that will get you the best results is to make your value of L as long as possible. And L is the distance between where you clamp the wire at one end, using a couple of blocks of wood that you then kind of G-clamp onto the desk, and you've got to maybe wrap the wire a couple of times around the end to actually stop it sliding through. So what you want to do is make this value of L as long as possible. So L, if you can, should be, well, at least over a metre, maybe a metre and a half, 2 metres. I've then put a piece of tape around the wire, which acts as my marker, and I've got my ruler just held close to the wire as well to reduce any parallax errors. The wire then goes over a bench pulley down towards my mass at the bottom down here. And something which is really important is that if you're going to do the experiment, you need to use safety goggles. The reason being that if this snaps, it tends to go without warning. And then if you imagine that thin piece of copper being dragged across the surface of your eye, kind of basically like a bag of water being burst, you don't want to be that person, okay? So when the wire goes, it properly flings out, so you need to wear safety goggles. The other thing you need to do is to make sure that you cushion the mass. If it does break, this doesn't, again, hurt anybody's feet or, you know, crash down to the floor too much. So pretty much that's all the equipment that you need. What you can then do is start kind of setting up the equipment, and then as you load it up, what you'll find is that this gets longer and longer as the wire is being drawn out. So when it comes to measurements, what you need to do is think about increasing the mass, you know, from 0 maybe up to 1 kilogram. So we've got the mass in kilograms, and then we have my extension, which I'm going to measure in meters. So again, always use meters for the extension. Now what you might find is when you put that first mass onto it, and again you've got to have a nice twisted bit at the end of the wire to kind of hold the mass securely. When you first put that maybe 100 grams onto it, you'll find that you get quite a big extension as that wire unkinks. That does not matter, because what you're going to be doing is you're going to be plotting a graph and looking at the gradient, not the intercept. So sometimes what you find is you get a big extension as the wire kind of just straightens out, and then you get a very, very small extension. And this is nothing wrong with that, okay? But you know, you're pulling a piece of metal apart. You're not going to have big extensions. So you measure the mass, you measure the extension, and what you can then do is plot a graph like this. So you have a graph of extension against the tension or the weight that you've added to it. So this is m times g in newtons. And what you should get is a straight line. And again, if it doesn't go through the origin, it might be shifted up or to the right perhaps, because you have that unkinking initially. Well, when you've kind of got a nice straight line here, and you want to avoid any bits at the top where it's starting to kind of go into this kind of plastic deformation, you should realise that the gradient is equal to E over mg. And you can use this gradient that you've just calculated to work out Young's modulus. So previously in the video I said that Young's modulus is equal to mgl over ae, and if we think about what this means here in terms of the gradient, we can also write that the Young's modulus is equal to L over A multiplied by the gradient, because the gradient is equal to E divided by mg. What that means is that once you've worked out your gradient, you can basically, you have your starting length of the wire, you have your cross-sectional area of the wire that you've calculated. Again, this has to be in square meters, so convert any distances or diameters from millimeters to meters, you'll have a very, very small area. And when you do that, you should then find that you have a very large value for the Young's modulus. And typically, Young's modulus for copper is in the order of 117 gigapascals. So you should be having a number, something times 10 to the 11 when you actually work out the Young's modulus for this material. So hopefully that kind of gives you a brief introduction to the topic. Again, the two safety points are that the wire may snap, so you must wear safety goggles, and also the weight may drop down in case the wire does snap, and therefore you need to cushion it. But I hope that helps, and good luck with your practical work.